So it says a ball is released at the top of a track that includes a vertical loop as shown. Rather than sliding down the track as in earlier examples, like in previous units, the ball is now rolling without slipping. The mass of the ball is 400 kilograms, and the radius of the loop is 10 meters. The radius of the ball is 50 centimeters. Okay, so maybe the ball is released anywhere above here. And then we need to find out how's it moving on the loop-to-loop. How did we do it old school? How did we know how fast it was going? Because that's question A. How fast is it going? 1/2 mv squared is the kinetic energy. Okay. How did we find critical velocity? Ooh. Yeah, when force normal is 0. So there's this net force. Ooh. Forces. We should probably look at the fact that there's forces here. What do you want to call that arrow? What's happening to everything? Gravity. So force gravity, or mg, is pulling it down. And the other active force on it, well, if it's moving fast enough, it will have a normal force. That's a fact that the track has to push it down. But we're looking where the force normal actually equals 0, where we're not pushing into the track any extra. In fact, it would just kind of float along there and roll along there without pushing on the track at all. If it was going any slower, it would fall. If it was going any faster, the track would have to push to help keep it on track. So that means our net force is equal to mg plus force normal, but we just said that this is going to be 0. mg. And our net force in this case is the force that also keeps us into a circle. And it also keeps us in a circle. So that would be MA, how it moves, right? Yeah. Or MAC. So MA is equal to mg. And if we're looking for some speed, could that speed just be v squared over r? And so when I move everything away from v, what do I get? V equals root RG, just like the old days. Okay? And even though some of you used that wonderfully on your test, some of you forgot that you had to prove it, or maybe you just didn't have time to write all that jazz down. But this is part of the starting points for where we are. Now, when I look at this problem, I also was worried because there's a radius here and a radius here. Which one is it, the loop or the ball, that I had to worry about for this speed? The loop, right? Okay, so this is the distance of the loop, 10, and g is 9.8. And so that's practically like 10 times 10, and then we take the square root of it. V equals a little less than 10 and a little more than 9.8. That's the speed. Okay. Now, you also said that the speed we can find in k. That kt equals 1/2 mv squared. So where are we really going with this? For how do we find the height? So now we're talking about the conservation of energy. Energy initial equals energy final. There are 4 pieces of the energy that I need. What kind of initial energy do I have if the ball starts up here? Okay, and it's not rolling yet, right? We just put it on the track. So we have mgh, and that's at the initial point. What about when we're over here in the loop-to-loop? Yeah. Right. So if I have both, I have mgh final, and then I have both types of kinetic energy, not just one. And so now instead of just saying 1/2 mv squared, I also have to worry about 1/2 I omega squared. And so there are my 4 parts of energy. The fact that all the energy came from a potential energy, that I'm taking that potential energy and, well, even though I use it all to get down to the bottom, it turns back into potential energy as it rolls back up. And then we know that it's in motion still to keep it on the track, and that it's still rolling because it's in motion. We could tie these two at the hip because the way it's rolling is based on its size. You've done that plenty of times at this point. Yeah. So we could take this I and say, uh-oh, it's a ball. So 2/5 mr squared, and then the omega becomes v squared over r squared. And we have the cancellation of our r squareds. I'm going to go ahead and cancel out those 2's as well. So I'm looking for my height that I need to launch it at. I've got mgh equals mgh final plus 1/2 mv squared plus 1/5 mv squared. Do we have the mass?
Yes.
We're looking for the height initial, so we have m, we have g. We're looking for our height initial equals m. Can I cancel out the m's? Yes, I can. Good job. You could cancel out the m's. I don't want to. You are so brilliant. You will cancel out the m's, and then in a later problem, when you get to part D, it's going to ask you about the energies, and you're just going to be like, oh, I've got to multiply all the m's back in to each and every part. So I'm actually saving you time in the long run, okay? So I get it. You're brilliant. You want to cancel out the m's. You could. But I trust me, bro. What was the height final? Uh-oh. What's 20? How'd you get 20?
Radius is 10.
Yeah, so this circle has a radius of 10, so it's got a diameter of 20. So to get from the bottom to the top is the full diameter. 20. We have 1/2 400. I feel like we solved for this speed. Yeah, 9.9 squared plus 1/5 400. 9.9 squared. Also, I could have added these together too, like the proportion of them. But we're going to need them separate anyway. So 400 times 9.8 is 3920 HIs equals 400 times 9.8 times 20. That's 78,400. 0.5 times 400 times 9.9 squared is 19,602. I feel like a car salesman calling out these numbers in this order. Like those classic commercials when TV was like, 7840.8. I add all 3 of those together, divide by 3,920, and then I got like 27.0008. which probably just means it's 27, and that the rounded 9.9 was that weird extra decimal. So it's 27. You're right. 27.
Okay.
Which means it only fell. It's also the speed that I would calculate if it only fell that much. Oh, yeah. If it was just rolling. Right? Is that not true? But the reason why we do it the long way, and the reason why it was more convenient the long way, instead of just like canceling out the fact that this is going to be 20 and 27, the difference is 7. The reason why it's more important to do it the long way is, does anybody know?
Next tab.
Building character. Character being part D. Character being part D. It says draw an energy bar chart that represents the ball at point A and B. So if I'm drawing these bar charts and I have the actual access to the energy numbers, it makes it way easier. Okay? Point A. Point B. Point A. Where does all my energy come from? Okay. So I'm going to max out this bar. UG. And then everything else is 0. What's everything else? KT and K rot. And then this, what's the height of this for UG? It's 3920 HIs, which was 27. Fine, I'll do it. I'll build my character. No, because the last thing I did was nothing related to that. 105,840 joules. Okay. That's it. That's all we need on that chart, right? What zeros? Oh, yeah, sure. Yeah, no, you're right. 0 joules. 0 joules. Okay. Total energy still way up there. But we still need, and this is where we need to make sure that we have that initial, that about 70% of it is still UG. Right? We've only dropped 7 of the 27 meters. And then KT is maybe about 20% of it. And K rotational is like 2.5 times smaller, so close to like 10%, probably less than 10% of it. It has to be very decent, relatively drawn. So does it have to be proportional? Mine isn't. I mean, I didn't even use a straight edge right here. It kind of curves up, so I can't really tell you perfectly. But what can we do to make it known what factors we're putting on here? Yeah, label it. 7, 8, 400. 19, 602. And 7, 8, 4, 1 joules. Joules of energy. It's this right here. KT, K rotation. And then all of our charts should kind of add up to being that up there. The 105, 8, 400 ish. Wait, it doesn't?